In public health, data isn't just a snapshot, it's a story that unfolds over time. Whether we're tracking disease incidents, hospital admissions, or mortality rates, understanding the rhythm of that data is how we detect outbreaks and save lives. This is where time series analysis becomes a superpower. Today, we're analyzing a classic public health dataset: monthly lung disease deaths in the UK from the 1970s. Our goal? To decode the patterns of the past to predict the needs of the future. We'll start by loading our toolkit: ggplot2 for the visuals, forecast for the math, and ggfortify to help them talk to each other. We are using the LDeaths dataset. This represents real-world surveillance data, the kind of information a health agency uses to monitor a population. Let's look at the raw data first. Using the head command, we see the first 6 months of 1974. Notice the numbers. We started over 3,000 deaths in January and see a steady decline as we move toward June. This immediate drop off as the weather warms up is our first hint that seasonality is going to play a massive role in this analysis. Next, we check the class of the object. R confirms this is a TS, or time series, object. This is important because it tells R that these aren't just random independent numbers. They are sequential observations where the order and the timing matter. Because it is a TS class, R remembers the dates, which is why we don't need a separate date column in our data frame. Looking at the summary statistics, we get a sense of the scale. On average, about 2,057 people died monthly from lung disease during this period. But look at the range. The minimum is 1,300 and the maximum is nearly 3,900. In public health terms, that max value represents a crisis point, a peak month where mortality nearly triples compared to the min month. Our job is to find out when and why those peaks happen. Finally, we define the boundaries of our study. The data starts in January 1974 and wraps up in December 1979. With a frequency of 12, we confirm this is a monthly cadence. This gives us exactly 6 years of data, enough to see if the patterns we observe are consistent year over year, or if 1974 was just an anomaly. Let's get our first look. A basic line plot reveals a clear, almost rhythmic sawtooth pattern. Are deaths increasing year over year? It's hard to tell just by looking. Let's take a close look at what this chart is telling us. We are seeing monthly deaths from lung disease in the UK over a 6-year period, from 1974 to 1979. Each point on the line represents 1 month, and together they form a continuous story about how these deaths change over time. The first thing we notice here is the rhythm. This is a classic sawtooth pattern. Notice how every year follows the same dramatic arc. We start high, plummet toward the middle of the year, and then climb right back up. But take a look at early 1976. See that massive spike? It towers over the other years, nearly hitting 4,000 deaths. In a public health context, that's a signal. Was it a particularly harsh winter? A secondary respiratory outbreak? This plot doesn't tell us why, but it tells us exactly where to start investigating. To get a better look at that rhythm, we use a seasonal plot. This is like taking our 6-year line and cutting it into 1-year strips, then laying them on top of each other. Now we're looking at the data in a slightly different but very powerful way. Instead of showing time continuously, this chart reorganizes the same information by month of the year, with a separate line for each year from 1974 to 1979. Think of it like stacking all the years on top of each other so we can directly compare January to January, February to February, and so on. The story here is even clearer. Look at the U shape. Mortality is consistently at its lowest in August and September. But once we hit October, every single year begins a steep climb. By layering the years, we can really see that 1976 outlier we spotted earlier, that green line peaking in February. While most years are hovering around 2,500 to 3,000 deaths in late winter, 1976 shot straight through the ceiling. For a health administrator, this view is a blueprint. It shows that while the timing of the surge is predictable, the intensity can vary wildly. This is why we don't just plan for an average winter, we plan for the possibility of another 1976. To see what's really going on, we decompose the data into three parts. One, the trend, the long-term direction. Two, the seasonality, the predictable yearly cycle. Three, the remainder, the random noise. Now we're looking at one of the most insightful views of the data, a time series decomposition. At the very top, we have our original raw data. It's chaotic and jagged because all the different forces, the season, the long-term changes, and random events are mashed together into one line. Next, look at the seasonal component. We've essentially calculated the average swing for each month and isolated it. Notice how perfectly consistent this is. It represents the predictable burden on the healthcare system, that rhythmic winter surge we've come to expect every single year. Now look at the trend. This is a revelation for public health. By stripping away those distracting seasonal spikes, we can finally see the big picture. Notice how deaths were actually climbing until 1976, but then began a steady multi-year decline. This tells us that beyond the winter flu seasons or cold snaps, something was fundamentally improving in public health or air quality in the late 70s. Finally, we have the remainder. This is the leftover noise after the trend and seasonality are removed. Remember that massive 1976 spike we saw earlier? You can see it clearly here as a huge vertical jump. Because it shows up in the remainder, we know it wasn't just a normal seasonal event or a long-term trend. It was a unique, unpredictable anomaly that required its own specific public health response. Instead of seeing this as one complicated data set, we now understand it as a baseline trend we want to reduce, a seasonal cycle we can prepare for, and unexpected shocks we need to monitor closely. That's incredibly powerful. Because in public health, the goal isn't just to understand the past. It's to separate what's predictable from what's preventable. You'll notice that in our previous plots, the swings between summer lows and winter highs seemed to get more extreme as the numbers got larger. In statistics, this can make our models unstable. To fix this, we apply a logarithmic transformation using the log function. This stabilizes the variance, making the patterns easier for our model to digest without being overwhelmed by the big spikes. Take a look at the y-axis now. We are no longer looking at raw death counts, but the log of those deaths. By squashing the scale, we've effectively stabilized the variance. Notice how the peaks and valleys now look more uniform in height compared to the original series. In public health modeling, this is a crucial step. It ensures that our mathematical model isn't overly influenced by the massive spikes of a bad winter while ignoring the subtle patterns in the quieter months. We've leveled the playing field, creating a much cleaner signal for our ARIMA model to analyze. Now, we move to modeling and the brain of the analysis. We use auto.arima. Think of ARIMA like an automated scout that tests hundreds of different mathematical combinations to find the best fit for our lung disease data. Now we are looking at the output from an ARIMA model, which is designed to capture patterns in time series data and use them to make informed predictions. But instead of just reading numbers, let's unpack what this actually means in a public health context. First, the model selected is ARIMA 002 to 1012 with drift. That may look technical, but here's the intuition. The model includes moving average components. That's the MA2 part, meaning it uses recent random shocks or surprises in the data to improve predictions. It includes seasonal components, the 2, 1, 0, 12, meaning it explicitly models the yearly cycle we observed earlier. The 12 confirms we're working with monthly data and yearly seasonality. The drift term represents a gradual long-term change over time. This model is acknowledging two key realities. Lung disease deaths follow a strong seasonal cycle, and there may also be a slow underlying shift over time. Now let's break down the key parameters. MA1 and MA2, these describe how recent unexpected changes influence current values. SAR1 and SAR2, these are seasonal effects, how values from previous years influence the current year. Drift equals minus 5.53. That negative drift is especially interesting. It means on average deaths are decreasing slightly over time, by about 5 to 6 deaths per month after accounting for seasonality. This aligns with what we saw in the trend component earlier, a slow improvement over time, possibly due to better treatment, prevention, or environmental changes. Now let's talk about how well the model fits the data. Sigma squared variance of errors, about 56,263. This tells us there is still variability the model can't fully explain, which is normal in real-world health data. Akaike Information Criterion, or AIC, AICC, BIC. These are model selection criteria. Lower values indicate a better balance between accuracy and simplicity. The model was chosen because it provides a strong fit without being overly complex, which helps avoid overfitting. Finally, we look at how well the model performs on the data it was trained on. ME, mean error, approximately 10.7. Very close to 0 implies little systematic bias. RMSE, approximately 207. On average, predictions differ from actual values by about 200 deaths. May, approximately 126. The average absolute error is about 126 deaths. MAPI, approximately 6%. Predictions are off by about 6% on average. MASE, approximately 0.54. This is important. Values below 1 mean the model performs better than a simple baseline model. A CF1, approximately 0.02. Residuals are not strongly correlated, a good sign the model has captured most patterns. Putting it all together, the model successfully captures seasonality, which is the dominant feature. It accounts for short-term fluctuations, it identifies a slight downward trend in deaths, and it produces reasonably accurate predictions, with about a 6% average error. The model confirms what we suspected. Lung disease deaths follow a strong seasonal pattern, but it also gives us something more powerful, a reliable way to forecast the future and plan ahead. But before we fully trust our model's predictions, we need to look at the residuals. Ideally, these should look like white noise, just random scatter. If there's a pattern left in the residuals, it means our model missed something important and our forecast might be unreliable. Let's examine the diagnostic plots for our ARIMA model to assess how well it fits the data. Starting with the top panel, we see the residuals plotted over time. Ideally, residuals should behave like random noise, fluctuating around 0 with no clear pattern. In this case, most of the residuals are centered around 0, which is a good sign. However, we do notice a few large spikes, particularly around the mid-1970s. These may indicate unusual events or outliers that the model does not fully capture. Moving to the bottom left panel, we have the autocorrelation function, or ACF, of the residuals. This helps us check whether any temporal structure remains in the residuals. Most of the autocorrelation values fall within the blue confidence bounds, suggesting that there is no strong remaining autocorrelation. This indicates that the model has done a reasonable job capturing the time-dependent structure in the data. Finally, the bottom right panel shows the distribution of residuals. Ideally, this should resemble a normal distribution centered at 0. Here we see that the residuals are roughly centered around 0, but there is some skewness and a few extreme values, which aligns with the spikes we observed earlier. Overall, these diagnostics suggest that the model fits the data reasonably well, although there may be some outliers or extreme observations that are not fully explained. In practice, this level of fit is often acceptable, especially in real-world public health data, where variability and unexpected events are common. Now, moving on to the Ljung box test. The Ljung box test is basically asking a very specific question. Are the residuals independent, or do they still contain patterns over time? In other words, are the leftover errors random, or are they still predictable? Here's what we see. Q equals 9.34, degrees of freedom equals 10, p-value equals 0.5006. Let's focus on the p-value because that's the key. In the world of p-values, this is a bit counterintuitive. Here, we actually want a p-value greater than 0.05. Our result is 0.5006. This high p-value means we fail to reject the null hypothesis, which is a fancy way of saying, yes, our residuals are indistinguishable from random noise. Our model has officially passed its checkup, and we are cleared to forecast. Now, we use our model to generate a forecast for the next 12 months. This is the moment where our analysis turns into actionable public health intelligence. Looking at the plot, what you're seeing at the end of the timeline is our 12-month forecast for lung disease deaths in 1980. The blue line represents our point forecast, the single most likely path the data will take based on historical patterns. Notice how it perfectly captures the anticipated seasonal dip in the summer and the rise as we head back into winter. It tells us that we should expect a peak of roughly 2,700 deaths early in the year, which is significantly lower than that terrifying 1976 spike, but still a major burden for the health system to manage. But in public health, we don't just bank on a single number. Look at the shaded gray areas. These are our confidence intervals. Think of these as our safety margins. Even if the blue line is off, there is a 95% chance that the actual deaths will fall within that lighter shaded zone. For a hospital administrator or a policymaker, this chart is a planning tool. It allows them to say, in the worst case scenario, we might see 3,000 deaths in January. Do we have enough oxygen, beds, and staff to handle that upper limit? By visualizing uncertainty this way, we transition from guessing to evidence-based preparedness. And there you have it. From raw surveillance data to a future-ready forecast. In this video, we explored time series analysis, focusing on trend, seasonality, decomposition, and how to generate forecasts for public health data. In the next video, we'll shift into one of the most powerful tools for analyzing observational data, propensity score matching. This method helps us reduce bias and make fair comparisons between groups when randomized experiments aren't possible, which is extremely common in public health research. You'll learn how to simulate more reliable comparisons, improve causal inference, and make your findings much more credible. Subscribe and stay with the series as we continue building advanced real-world analytical skills in R for public health.